We start again with Litz Vivas from Ohio State University, who will speak about local dynamics of reduced saddle node biholomorphism.
Thank you. Thank you very much to the organizers of this wonderful conference for the opportunity. I gotta say that INPA is a very special place for me in Rio de Janeiro. The first time I came here, I was 14, so that was a long, long time ago. And it's very, very nice to see old friends and meet new friends too. And so, yeah, thank you very much. All right, so I'm going to talk to you today about local dynamics. And I know that there is many different types of dynamicists in this meeting, and I'm going to talk in the context of complex dynamics, a specific type of complex dynamics, a specific type of area inside local complex dynamics that it is parabolic points. So I want to motivate all of the things I'm going to talk about. So I'm going to give you a little overview of what people have done in dimension 1, what it's known. So I'm sorry if this part is a little bit boring for the experts, but I think it'd be good as a starting point for us to be on the same page. So what I'm working on is looking at germs of holomorphic maps. By this notation, I just mean that this function has to be defined in a neighborhood of this is 0. It just can be any fixed point, but by translation, we can always put it at 0. And it has to be holomorphic in a neighborhood of that point. Okay? And so let me write here n, because n is going to be bigger or equal than 1. So our starting point is to try to understand, at least locally, one starts in the neighborhood of this point where my function f is defined, what happened to the orbits. And of course, the history is quite well understood for n equal 1, and maybe also for n bigger or equal than 2 in certain cases. So that's what I'm going to summarize maybe a little bit first. And I also note that in the audience, again, we are all the time conjugating and looking at things like this. So we want to emphasize that the classification varies widely if you allow conjugations that are only topological and homomorphisms, or if you allow formal objects, or if you require that your conjugation has to be analytic or holomorphic. Okay, so just as a initial case, what happens when n is equal to 1? These results are classic, I should say. I will not even give names. And just to be, okay, let me just say F local diffeomorphism, okay? Local invertible. All right, so it is a classic result from, I don't know, 18th century maybe, that if the derivative of this is not in modulus equal to 1, then locally you can always linearize holomorphically. Okay? So there exists a conjugation holomorphic it's just a linear map where lambda is the derivative. Okay, so because I force my map not to be locally invertible, then the derivative can never be 0. So in modulus, you can just have that it is going to be either less than 1 or larger than 1. So it's either a contraction to that fixed points, or all the points are escaping that neighborhood. These kind of results actually are very useful. Well, as we know, this kind of maps, for instance, when lambda is less than 1, you obtain a basin of attraction that is local. If your map that you started with was a global map, then you obtain a 2 component, etc. All right. when the modulus of lambda is equal to 1, and as we saw in the last talk, things can be very complicated. So you have that either you're at irrational rotation. Okay, so theta is P over Q. This is a rational rotation. Or if theta is not rational. Then here, okay, so again, I just want to say complicated because we have different cases. As we saw, the dynamics might vary strongly depending on the arithmetic properties of these irrational numbers. You will have bounded irrational numbers, or Kremer, et cetera, and then you have different dynamics that can happen or can be conjugated or not. Again, deep results of maybe Jocose, but much earlier Bruno, et cetera, and of course people of the audience too are studying these very interesting things. So again, this case is complicated. I'm going to focus on a more classical case, which is the rational rotation. This actually already was explaining the nature of the topological classification was a work of Fatou. But yeah, maybe let me just write here, what do we know? Okay, so if lambda is e to the, sorry, I'm missing a 2 pi here, 2 pi I q. Then when you iterate q times here, your map, let's say map C, you're going to obtain lambda to the q times c, so you obtain c, plus higher order terms. Let me just write square, but in reality, you can start at c to the q plus 1. But just this specific first multiplier here, which is 1, which I didn't write down, that's actually the theorem of the setting on which I'm going to write it down as a theorem of Liu Fatou Flower. Okay? And what Liu Fatou say is that if you want to understand the dynamics close to this point, you have to look at the power expansion. So given f of z, given f, yeah. And look at the first term that doesn't vanish on the power expansion of f. So let's say I'm going to write here k t to the k plus 1. Sorry, sometimes I write the absolute value, sometimes not, but it just means that the higher order terms are coming. Suppose that this term is non-zero. Of course, that can happen starting at k bigger or equal than 1. That will be if you have a quadratic term, but if you don't have a quadratic term, then you look at the third order term. The only way in which you will have that they are all 0 is if you started with the identity, and that we know the dynamics. So if you look at the first term, then that's going to tell you a topological invariant about these maps, which is going to be that in close to that fixed point, 0, you'll have, let me just write, for instance, k equal 2 here. Okay, so this is going to be k 2. Yeah, I'm going to show you a little bit more about this in a second, but you have that there is going to be 2 pedals that are invariant. This pedal stays on itself, and where there is an attraction towards the fixed point, and there are 2 pedals that are repellent. Different color. Maybe I can try with this. And as I drew it, it doesn't seem like it tells you a lot, but actually these are very, at the moment, what I'm going to call a fundamental domain. In some ways, this can be fattened up. Okay? So this orange thing, I drew it like, sorry, not a very good drawing. And this also can be fattened up. And this blue thing, actually, it's bigger than what I drew it. What it turns out is that these big pedals, and again, there is not a really good consensus on the literature of what do we call the pedals, if the little part or the big part, but this big orange thing is going to be mapping into this smaller orange thing, and then everything is going to go towards the origin when you're in the orange petal. In the blue part is the opposite. This small blue petal is getting into that big blue petal, and it's escaping the origin. Okay? But together, there's K attracting petals, K repelling petals, and together, let's just call it U attracting I, U repelling I. And if you put out the union of all these, I should have used a different letter, but okay, well, here we are. Union of UI attracting, union UI repelling. We'll cover union the origin, because that's not in either. This is a neighborhood of that fixed point. Okay? So it's very good in the sense of, like, you can find out and understand what the topology is. And inside each petal, we have a way to know how fast the petals are going to the origin when they are the attracting petal, and when they are repelling, also how fast they are going away from the origin. As it was mentioned maybe on the last talk, it's going to be 1 over linear to the 1 over k order. Okay? The end iterate is going to be of about that size when you're going inside. All right. This doesn't say that this function, so observation or remark, f is not analytically conjugate to, say, the first term to this, but it is topologically conjugate to that, okay? But f is topologically conjugate to this. Again, you can find a conjugation that is on the realm of homeomorphism, but not analytic. And actually, the analytic classification, it's quite complicated. It turns out to be a moduli of basically other functions spaces. All right, so these are well understood in this dimension 1. And why do we want to know exactly about what happens here? Because, of course, when you're studying, for instance, say, moduli of functions or like quadratic polynomials, and you encounter a parabolic fixed point, you need to know what to do. Even though they are not that dense or anything like that, it's a condition that it's basically a closed condition. You still will need to encounter them. We'll find them. All right, so now I'm going to talk about what is known in dimension 2, or larger or equal than 2. So what if? So we're still on the same setup. We still, but maybe I should be a little bit more precise here. When I say 0, I mean the vector 0. Again, it doesn't have to be that the fixed point. You can always just conjugate it to that point, especially if you're in a local coordinate chart of any. All right, and so here we have some conditions. Now I don't have a derivative, but I have instead eigenvalues. So my eigenvalues of my matrix are lambda mu. Let's say, well, let's start at n equal to, okay? So then I will explain what is known or what it can be generalized or not to higher dimensions. Okay, and because of precisely of the condition that this is locally invertible, of course, they are both different from 0 in modulus. And there is also a similar situation, and this is again classical from Poincaré, et cetera, when they're both smaller in modulus than 1 or larger than 1, et cetera, except that when you move into higher dimensions, there is a problem, or there is an extra complication, which is based on the resonances of these two terms. One can be the square of the other one, and that has to be taken into account. But I'm not going to focus on that. Instead, as you saw, these two last cases in some ways are more complicated than the other cases, and the same thing happens here. When lambda and mu have modulus equal to 1 in some combinations, these things are quite complicated and not so well understood. Okay? One case in particular, which is the case that I'm going to focus on, which is maps tangent to the identity. Is the most resonant case that you can imagine. Resonances happen when one of them is power of the other. When both eigenvalues are 1, it's basically every term is resonant. So if actually this derivative term is the identity, we say F is a map tangent identity. And I'm just going to write it like this. And again, if you think about what happened in dimension 1, you don't want to conjugate to the linear term when you are tangent to the identity. The linear term is C. If you conjugate to C, you started with the identity. You want to conjugate to something that is maybe capturing more, which in this case it turned out to be the next order term, but that's only topologically conjugation. Okay? It's not the analytic conjugation. But it's okay. At least we want to know that, at least topologically what's happening. All right, so the similar can dimension 1. Maybe the first thing we should do is look at the power expansion and see what's the first term that doesn't cancel. Okay? So that is actually what I'm going to write here. But OK, maybe I'm going to write my new coordinate z is actually x, y, because now I'm in C2, remember that? So my power expansion should start here. And then the next term is actually two coordinates, because I'm going from C2 to C2. And I'm going to do as we did here, which was to write down homogeneous terms of degree k plus 1. I'm going to do the same thing here. I'm going to write all the homogeneous terms of degree k plus 1 in both coordinates. Okay, so let me actually erase this and just write pk plus 1 of z plus higher order terms. Where this one doesn't vanish, it's not 0. And it's bihomogeneous of degree k plus 1. All right. And so the same question stands. If you have if you write down this first term, can you determine topologically what happens to the coordinates just based on this first term? And it's not anymore good in the sense that there is not a theorem anymore like this theorem. It turns out that this is not going to tell you enough, but it can tell you still some things. And let me explain you what can it tell you and what has been studied. All right, so we're working now in 2 dimensions. This drawing that I did here was in 1 dimension. So now you should think about 2 dimensions, and now I will have, I could have pedals that are of 2 dimensions, or maybe pedals that are in 1 complex dimension like this, et cetera. But the first thing to observe is that this is a map from C2 to C2 that has by homogeneous degree k plus 1. So in some ways, it can be, and it is actually possible to transform it into a map of P1 to P1. And there, it's going to have some fixed points. And maybe it's those fixed points the ones that I'm going to have to check that are some kind of attractors or not. Let me write that down, actually, without going to the language of P1. So let's just say if you have a vector v, that is v1 comma v2, such that when you plug this pk plus 1 of v, you obtain a multiple of v. Okay, again, I want to explain that this if condition that this happens, if it happens for a vector, it happens for the double of that vector to v1 to v2 because of the homogeneity of this. So it's a different constant, okay? For some constant, we call this vector something special. Oh, some difference for some c. Then we say v is a characteristic direction. All right. Why did I, again, point out these specific vectors? Because they have a special significance that it's going to be the following lemma, is that if you have a orbit converging towards that fixed point, and it converges along a certain direction, it has to be a characteristic direction. So, lemma, let me just write it like this. If you have a trajectory of point Cn, xn, yn, and they are defined as, the iterates of my map, such that this orbit is going towards the fixed point, and the direction, again, of this orbit is exactly going towards this, just write like this. If yn over xn is converging to certain number c, okay, then 1 comma c is a time characteristic direction. So let me draw C2 now like this. Now this is a very hard task in my field to draw anything because it's C2, 4 dimensions, it's very hard to draw anything, so we have to use our imaginations here a lot. If you have an orbit of points, they are going towards the origin. And it turns out that tangentially, they are going, say, tangential to this first axis, axis C. Then it turns out that the direction 1, 0, that was a characteristic direction. That was a solution of this algebraic equation. This is an algebraic equation. It's going to have either, I guess, k plus 2 solutions or infinitely many solutions. So you always can find characteristic directions, and so they are important if there is something like this. All right, so this was kind of, there were many isolated examples of different maps which had some of these orbits. And it was only until about 1998 when Hakim, and about the same time also Ekal, maybe a little earlier, explained that actually whenever this characteristic direction, I used two C's for different things. Let me just write this theta, okay? 1 theta. For certain, let me just write it like this, for certain characteristic directions, we can always find pedals. Associated to it. Okay, let me attracting pedals. Let me explain this statement with a picture. Okay. Maybe actually with an example. It's even better because in this example, I can show you how you compute the characteristic directions and what is the condition that Hakim and Ekal introduce. So let's say you have this nice map, f of xy equal x plus x squared plus higher order terms, order 3, I don't know, say that you're working on some particular map and you encounter this and you want to know what is the dynamics of this map close to the origin. Okay, if you will just use one-dimensional dynamics, maybe you can say, okay, maybe everything is in here. I just use a two-flower here, and then I plug it here. But this order tree has cubic terms on y and cubic, etc., or a mix of x and y. So it's not that simple in general. So one way, again, what is that Hakim's theorem says is, like, look at the first degree two terms in this case, which are not vanishing. So this is my degree two term. I find the characteristic directions, and how do I do that? I have to solve this following equation. Find characteristic directions equal a constant times x comma y. Again, this is an equation that, well, two equations, x squared equals cx, 2xy equals cy. You're solving for x and y, okay? And you're going to see that the solutions are precisely when x and y are 1 and 1, 0, and 0, 1. And I think that's it. Okay? All you need to do is multiply this by y, multiply this by x, make them equal. And yeah, that's a multiplicity 2 solution. This is a multiplicity 1. Okay? Again, 1, 0, you plug it here. 1 squared, 2 times 1 times 0, you get 1, 0, which is 1 times 1, 0. And if you plug 0, 1, you're going to get 0, 0, which is, of course, a trivial multiple of 1, 0. In the language of projecting to the dimensions, what you found out was that this one was a fixed point, this was one indeterminate point. Anyways, this is going to be a good characteristic direction for Hakim. Why? Because what they mean here by good for certain, and let me just call it maybe the language that we know it, is non-degenerate. It's just going to mean that it is a fixed point, not an indeterminate point. Okay? This is a fixed point, 1, 0. This coefficient here was non-zero. So 1, 0 is a non-degenerate characteristic directions. And the other one is a degenerate characteristic direction. All right. So what's the result of Hakim or Ekal say for this map? Again, both their axes are complex lines. This direction 1, 0 admits a parabolic pedal. By that, again, I mean a one complex dimension. Let me just draw it like this. This is supposed to be one complex dimension, so two real dimensions. Analytic object in which every point here is being mapped to the point here and to the point here. But again, you should look at it, if you look at it from up, it's really a pedal. Okay? It has a real direction too. It's a pedal. But then later on, people kept asking about what about when you encounter the other type of characteristic directions? Do you still have pedals or not? Or also, the other question is, how about you want to make open sets? For which ones do you have an open set of two dimensions for which you will have an attraction? And so all of these things have been, like, in some ways, disjointly studied. I work myself on some of these questions for dimension 2, etc. But the most comprehensive, maybe, result at the moment, the most state-of-the-art result that we have, it's actually quite recent. So this is a theorem of Lopez Hernandez Rosas. Yes, and what I'm going to tell you later, it's also in collaborations with them. I think it should have, 2021 maybe, or 2022. They proved that actually it doesn't matter if you are a non-degenerate characteristic direction or degenerate. For every characteristic direction, there is either an attracting petal. And I'm focusing on the attracting part, but in reality, for every time you find attracting, there's always a repelling part too. Okay? Or a curve of fixed points tangent to this direction. Okay. So what you expected, what it's true, is that the dynamical directions do have a, or any characteristic direction does have a significance about what orbits can go towards it or not, unless you started with something fixed, in which case it's kind of trivially going to be a characteristic directions, and then you have that it is going to be tangent to it. But this says something only about a one complex dimension object in C2. Okay, it's very small. It's just, again, part of the story. And I should write here ideas on this proof. Hakim's, okay, so Ekhal's results are all using resurgence theory, which is a much finer theory, but related to summability in some ways, and what divergent objects can tell you, even when they are divergent. Hakim actually uses more functional analysis tools. She constructs some Banach space, some contracting operator. The Banach space is made of curves. The contracting operator tells you that if you have a fixed curve, you're going to have a fixed point. So these are functional analysis tools. And it works for any k, okay? So I wrote it for k equal 2 for functions from Cn 0. It works for any n bigger or equal to 2. Whereas these results, Lopez Hernandez and Rosas, it only works for n equal 2 because the technique that they use, it's basically as a resolution of singularities a la Camacho-Sat style for foliations, but in the realm of maps, in the realm of maps. Okay, so this uses resolution of singularities a la Camacho-Sat, but maybe I should say here first started or first done by, or first done and created and used by Abate in the context of maps tangent to the identity.
So the theorem is for dimension 2 or dimension 3?
Did I already what?
The theorem is for general dimension.
So this one is for general dimension. All of this is for dimension 2 only. Yeah. Again, because the tools are only available right now in dimension 2. Does that answer your question? Yeah. All right. This first done by Abate in around 2001. I think the first time I heard about it, actually, I was a student here, and Abate was visiting IMPA, and I think he got great inspiration here to actually construct this beautiful similar construction to Camacho-Sat. All right, what I wanted to tell you is what happens outside this curve of fixed points. How do you know how to complete the dynamics around a full set of a neighborhood on the origin? And that's still actually very much not completely realized. Again, what I have at the moment, or what we have at the moment, is when you do this resolution of singularities, you arrive to a certain number of models. And now we have basically a complete understanding of what happens in all these type of models. Okay? So this is basically our progress. So let me just write it out here. When we do this resolution of singularities, and let me explain you why is it different than the usual Camacho-Sat resolution of singularities, if you're familiar with that. It's similar, but at the same time it's different. So you're starting with a map F, that it is basically from 2 dimensions to 2 dimensions. And as I said, it starts with certain first-degree order term that is non-zero, higher order terms. Okay? The goal is to associate to this F a vector field X, so that F is the time one map of this vector field. For t equal 1. If we know the trajectories of this vector field, then we will know what happens with the orbits of F. This is, in some way, something that if we have one direction, then we have the other. But unfortunately, this X exists formally, in the sense that this is basically an equation on power series that you can always solve, but it almost never convergent or an. Okay. So you're not going to get a real X in which you can do all your classical dynamics of singularities tools, all your classical resolution of singularity tools as Camacho and Seth did. But this is the good news, is that a formal X also has a resolution of singularities. Basically, what they do combinatorically of creating all these typical models that you can obtain still happens. Okay? And so we're still going to have that there is just a certain number of models that exist. But like the question is, so what? Now you have certain formal models. What does that have to do with the original F that we started with? Well, it turns out that even though they are formal, the exponential of those formal objects is going to be analytic. And so we can still use this formal object, which is going to be, again, the resolution of singularities of this, to go back to my initial F that had was analytic to begin with, and it will have a resolution that is analytic too. All right, so let me write that here. So starting with F, you have your fixed point 0. And then what we're doing is basically blowing up this origin and getting a new, basically, here is going to be my exceptional divisor, which is going to be all fixed because this point was fixed to begin with. My characteristic directions will be around here, also fixed points of this blow up. And then the procedure says that you can just keep blowing up, etc. P1, and there's going to be an induced action. So this was the action of F. There's going to be an induced action here, F tilde. Here also F double tilde or whatever. That is actually just basically following what F is doing on each coordinate. But at the end, the theorem says that at the end, you obtain just certain models that can happen. So there exists a finite number of lobes where at each fixed point of F, whatever, triple tilde or whatever it's that your final model, we have only one of the following three cases. And here is a specific list of things that you can get. And in each one of these cases, I mean, this is the goal. If we understand the dynamics on a globally, not only on a pedal, but globally on a full neighborhood of the origin of each one of these cases, then maybe we know also some more things about my initial F on more than just one direction, but at least on a full neighborhood of whatever directions we're coming from. Okay? So the following three cases are called, very confusingly, non-degenerate case, Again, not to do with the same non-degenerate ante-Hakim. And the second one is called saddle knot case. There's two saddle knot cases. So I'm just going to write it here, saddle knot cosnake 1, saddle knot case 2. And I'll write it up on the board for you to just explain all these three cases and explain what has been done in each one of them with respect to like the dynamics of each one of them. Okay, so now I need to look at my notes. Dimension 2, I did this, I called Hakim. The resolution of singularities, sorry, yeah. Okay, so let me write the first case. Case 1, non-degenerate. Again, all it tells you is that when you blow up at a certain point, your fixed point can be written as this. This might seem familiar to the people who do holomorphic foliations. Or x plus 1. No, I'm just writing this down for completeness arguments. It's not like I'm going to work with these forms directly for you, not now. But it's basically, this is the non-degenerate case. This, as you can see, is going to have a similar weight at what the example that I gave you earlier, only that m is bigger or equal than 1 now. Similarly here. And the second case, which is the saddle knot, it's similar, but they just say that the first term is going to be just like this, similarly. But in the second term, a higher order can happen. And this creates extra complications. Okay? This is when n bigger or equal to, yeah. Did I write it here? N equals 0, it doesn't matter. Or the same thing, but with that y to the n. When you get to one of these models, you cannot, you can try to keep on reducing, but all you're going to get is one of the cases that you had before. Okay? You cannot keep on reducing any further. All right, so the theorem that we have is basically, and I didn't write down saddle knot case number 3, but it's basically with one of these A or B is 0. Okay? So what we have is here, or the way that this has gone is that our theorem basically says that if f is of saddle knot type, as I wrote it there, let me just write it case 2, okay? Case 2. Then on a neighborhood of the origin, we understand the complete of the origin. We have n petals. Let me just write it m petals in the first case. 1 complex dimensional. We also have 2 complex dimensional open domains or open domains where each point, they say u, I, then m of them, where each one of these p is going to be going towards the origin, and it's actually tangent to this direction. And we're going to have similarly repelling open domains, also where the inverse map of this is going further away from the origin. And repelling domains. And together with this attracting orbit, let's say m is equal to 1 only. Okay, so I'm going to have attracting part, a repelling part. I'm going to have I'm going to draw it like this. This is going to be my attracting domain, my repelling domain maybe. But we also know what happens outside this part, okay? And outside, let me call it V, and outside of this, we have a saddle type of orbit, in the sense that you're never going to stay for any point in V. You stay finitely many iterates stay in the stay on my domain, on my neighborhood theory. Backwards and forwards. So we know that you cannot have other attracting random orbits, for instance, that go on their own, not related to this. We know that you cannot have other repelling orbits in that way either. Okay, this is going to be backward and forwards for these other maps. So we have a complete, again, understanding of what happens on a full neighborhood. This actually completes in some ways this non-degenerate case that had been done before by Rosas and Lopez-Hernandez, in which they actually don't get any of this saddle behavior. They are going to get a condition that tells you that it's all attracting or repelling, or nothing is attracting or repelling. So again, we're just doing progress here about how to complete the picture of the full, of all the possibilities classes. This is all very much particular for n equal 2. For higher ends, the similar tools that we will try to use, which is vector fields in higher dimensions. There are many counterexamples there that have been studied. In fact, more than examples sometimes, different types of resolutions. Some of them work, so we do have some work about that, but nothing in a full neighborhood of the origin, not yet. All right, I'm gonna end here. Thank you so much.